Okay, in this video we're going to be continuing with sorting algorithms. We created a sort template for each one of these algorithms, and we have done bubble sort and insertion sort, and now we're on selection sort. So I've copied over my template to selection sort, and we have a way of getting the numbers either from the arguments, or we can collect them in a loop from standard input. We have this swap function, and this is the function that's essentially our sorting algorithm. Okay, so this function takes in a list of unsorted numbers, we duplicate the list and return a sorted list of those numbers. Alright, and then down here we print out the information, unsorted, sorted, and then we confirm whether or not we succeeded by having a Python sorted list. So Python sorts the list, and then we compare our list to the Python sort list, and if we succeeded, we print out sort succeeded. If not, sort failed. Okay, so selection sort. What is selection sort? We've talked about bubble sort and insertion sort, and selection sort is a little bit different. Each one of these sorts is slightly different. One of the things that selection sort works to minimize is the number of swaps. Okay, so for bubble sort, we remember we would take this number and the next number, and if they are out of order, swap them, and then look at those two and swap them, look at those two and swap them, swap, 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 and at the very end one item would be at the top. We'd go through and keep swapping. So there are a whole bunch of swaps in bubble sort, and same with insertion sort. Insertion sort, though, had a nice way of since it maintained a pre-sorted list at the beginning, sometimes you wouldn't need to iterate all the way through, you could just stop. And so there were a limited number of swaps in that, but there was still a fair number. Okay, one of the things selection sort does is basically there's only one swap per iteration through the loop. Okay, so what we do is with selection sort is we start with our starting value, and then all of the other values we iterate through and find the smallest one. So we have to check to see, is this the smallest value? Is this the smallest value? Is this the smallest value? We check to find that, and once we find the smallest value, then we do one swap. And now this item to the left, this would be a 10 over here, right? So this item to the left is the smallest item in this list. Now we go through the rest of the list. Well, now we're on this item, and we want to find the smallest item in this list. So we have to do a lot more compares, but we only have to do one swap. Okay. Now the advantage here is it depends on how many CPU cycles a swap takes. So some of these algorithms perform differently in different cases, right? So depending on the input data, and also in some circumstances, for example, if a swap happens, in reality, a swap would actually take several CPU cycles. It would, if we look at the actual code, right, we are accessing an item from memory, so that might be one unit of work, storing an item in memory, that might be another unit of work, and then we're accessing an item in memory again, storing an item, accessing and storing. So that's 3 and 3, so that's 6. So swap function might actually be like 6 units of work, and it really depends on your CPU and how everything, how the CPU encodes some of these messages, right? Encodes some of these operations, I mean. So if swap was expensive, maybe this swap function takes 100 units of work. Well, you'd want to minimize that swap function. Comparisons might just be 1 unit of work. All right, and again, this depends on the CPU, but generally speaking, comparison would just be 1 unit of work, 1 CPU cycle, compare 2 numbers, and get a result. And so what selection sort does, since comparisons should only be 1 unit of work and a swap might be more like 6, it minimizes the number of swaps for efficiency's sake. Okay. Now this all depends, of course. You know, if you would want to use this algorithm, it would depend on your CPU, and you'd have to look into some of that. And it would also depend if this is a really efficient algorithm. We have to check the time complexity at the end to see if it's efficient or not. N squared in general is not considered efficient. So the last two algorithms we've tried have both been n squared, which is not particularly efficient. What we really want to look for is something that's log n. All right, so we'll check back and talk about the time complexity after we go ahead and finish up the algorithm. Okay, so the basic idea is we start with this first element, the index 0, and then we search through all of the other values and try to find something that is less than this value. If we find something that's less than that value, then we do one swap. Okay, then we move on to this next element. And we find the next smallest item, right? So the next smallest item in the list. So at this point, we know 10 is the smallest in the entire list. So we can kind of think of that as its own separate sorted list. Now we only have to look at these items. We find the smallest item in here and then swap once, right? So this is kind of like the opposite of bubble sort, where we ended up with the highest value, the highest number at the end, except bubble sort did a whole bunch of swaps to get there. This scans and only swaps once, but it finds the smallest item. Okay, so then we're at 33, we scan all these items, find the smallest one, and swap 33 with that smallest item. Now we have another item of our sorted list, and we just keep doing that. Okay, so what we're going to have to do, again, we're going to have two kind of for loops and try to think about the indice values, our indices of the for loop, the index values, right? So initially, you know, the first value that we're looking at, that's index I equals 0. We're looking at this number 14, right? And then we're going to scan all of the other items. Okay, so let's see if we can code this up in Python 3. All right, so here's our sort algorithm, and again, this is selection sort. Now the reason, again, it's called selection is we find an item, we're starting here, and we have to scan and select the item that we want to swap, right? So we've selected 10 as the first item, and so we swap. Then we look at the remaining items and select the lowest one. We've selected 14 and swap. Scan and select the lowest one and swap. So that's why it's called selection sort. All right, so as usual, we're going to have some sort of for loop for I in range, and we do not know the bounds of this for loop yet, so we'll leave it blank. But that I, we might use that I, and we'll say that index is 0, and it'll go all the way to, you know, the length of the list. So we'll start with that, and we might have to change it. So length of our list. So sorted is the list of numbers. It's a duplication of our unsorted list. So it's not sorted yet, but by the end, it's going to be a sorted list. All right, so for I in range length of sorted, so that means I is going to become each one of these items. So let's say we go all the way down here, and we look at 35. We want to scan through what's the smallest item. 35. Okay, so move on to the next one, 42. We scan the remaining two items, and we see that 42 is the smallest item. So this whole thing would be the sorted sublist. Then that last item, we don't really have to do anything with, because by default, it's going to be the largest item. So we don't need to do any compares, really. So this loop here, for I in range length sorted, we can actually say sorted -1, because we don't really need to do anything with that very last element. All right, so we're going to have that loop, and then similarly to the way a lot of these other algorithms have gone, we have to scan through another list of items that gets smaller and smaller, right? So the new list, we're going to have some other loop for j in range. This new loop is going to change depending on what iteration of this outer loop we're on. The first iteration of this outer loop, j is probably going to start at 1 and go to the length of the sorted list. All right, so that would mean I starts out here on the outer loop, and then j starts out one more than I, right? So actually that should be I plus 1. So this will start out at I plus 1, right? So one more than wherever I is, and then we go all the way to the end of the list, the length of the sorted list, right? So the range function never includes that final number. Let's see. So the length of the sorted list, that number is not included. 1 minus that is. So that's the last valid index of that list. Okay. So basically, the first time through the list, I is 0, and then j is 1, and this inner loop goes from this item to that one, 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 right? And then we will have selected, we haven't done that yet, but we're going to have to select one of these numbers as the smallest item and swap it out. Okay? So if we want to keep track of the smallest item, we're going to need to have a variable. In the other sorting algorithms, we didn't need an additional variable. So we're going to have to keep track of this variable, and it's going to be the index of smallest of current smallest. So as we're scanning, we might find one small number, but then we might find another one, right? So as we scan here, 14 it will be our smallest, but then we scan, we see 10 is smaller, we scan. Okay, so we only saw one number that was smaller, but over here we can scan again. Like if we get past 14, let's see if this isn't a good example of that, but you could imagine that if we had a number 1 over here, 14 would start out as the smallest. You scan and scan, you find a new smallest, scan and scan and scan and scan, and then you found 1, and that would be the new smallest. So you have to update the smallest periodically. Okay, so this is the index of the current smallest number, right? So the index of the current smallest, we start out as I. Okay, so we're going to say the current smallest number is 14. And then we're going to look through the second loop. This is going to be j, and j is going to be each one of these numbers. And we're always going to compare the item at index j to our smallest number, our current smallest. Okay, so for j in range, starting at I plus 1 to the length of the list, what we want to do is we're going to have an index. The index to check is j, right? So what we want to do is, if the item in our sorted list at j, right, that's the index of the item that we're checking, j, and so first time through the loop, that's going to be the index 1, which would be the element 33, right? If that element is less than the element at index of current smallest. So basically this is saying if the element at index j is smaller than what our current smallest is, then we have a new smallest. We need to set this to a new value. Okay? So this is no longer the index of the smallest, because we found one that's smaller, right? The item j, the item at index j is smaller. So that means the index of the current smallest is now going to be set equal to j. And that's only if the item at index j is less than the item at index of current smallest. Right? So the current smallest is 14. We scan, is 33 smaller than 14? No. Is 27 smaller than 14? No. Is 10 smaller than 14? Yes. So now we have a new current smallest. And then we keep scanning through the list. Okay, so that's this if statement. Right? Right, what else do we need to do? So if we scan through the list, it could be that the item we started with was the correct, or was already the smallest item, right? 14. Let's say we had an item over here, the number 1. Well, the number 1 would be the smallest, right? So if that's the case, we don't need to swap. But if it's not the case, we do. So if index of the current smallest number, if that does not equal I, which is what it started as, right? This is basically saying if it's still I, do nothing. But if it's not I, if it's changed, that means we have a number that's smaller, so we have to swap. Okay, we started out this index equal to I, and the only place we change it is here. And we only change it if we found a new smallest. So we only need to swap if we found a new smallest. We don't need to swap this number out for itself. That's a waste of computer cycles. All right, so if the index of the current smallest does not equal I, then we swap. We take our sorted list and the index of the current smallest, and we swap that with whatever's at I. Right? So if these equal the same thing, then I'm swapping sorted, and it would be like swapping I and I. That's not going to do anything. It would still execute the computer cycles, but the list would end up the same, which isn't helpful. Okay? So we only want to swap when we need to. So that's what this check does. All right? So that should basically be it. And we're going to want to add in our work. Okay, so we want to, what we arbitrarily chose for work, we're saying +1 work, 1 unit of work for comparisons. And then down here for a swap, we'll say work plus equals 1. And this is for the swap. Swaps. All right, so we can run this and see Python 3 selection sort, and we can take a look at the numbers and see what kind of numbers we want to use. We've got 14, 33, 27, 10, 35, 19, 42, and 44. All right. And we see that the sort succeeded, right? And 33 units of work to sort. All right, let's compare this with the bubble sort. Okay, so bubble sort had 35 units of work to sort. Now let's play with this a little bit, and let's assume swaps takes like 6 units of work. Okay, instead of 1 like we had defined. And in bubble sort, I'm going to change it to, we're going to say the swaps are 6 units of work. Okay, so keep in mind the last time we ran it, selection sort had 33 units of work. It was still less than bubble sort. Bubble sort had 35. But now we've changed the work to simulate a swap costing more, right? And so we can take a look at this and see how it changes. So let's look at the selection sort now. Let's make sure we saved our files. Yeah, we're good. Okay, selection sort. So selection sort was 58 units, and now let's try bubble, and it's 70 units. So you see it went up a bit more. So before it was only 2 units of work more, and now it's like 12 because the swap is more. And this, it partly depends on the list itself, because some algorithms you're not going to have to swap very many items, right? For example, in bubble sort, if the list is sorted to begin with, then you're not going to have to swap at all, right? You compare these 2 items and they're in the correct order. These 2 items, correct order, right? If it was an ordered list. So in that case, there wouldn't be any swaps. If it was in the opposite, a reverse ordered list, then there would be swaps almost every single search. right? Almost every iteration. So it sort of depends on the lists, but you can get a better idea. The reason we're adding this work function is because, or keeping track of this work, is because different operations have different costs. And you need to be thinking about that when you make algorithms. What is the cost of this thing that I'm doing, right? If I call this swap function, is it cheap or is it expensive? If it's expensive, I want to use it sparingly. I want to make an algorithm that only executes this in rare cases, right? If this is cheap, I can use it as many times as I want, right? So we always have to weigh the cost of using a function, the cost of an algorithm. Okay, and so that's what we're getting into with this work, keeping track of it. I know it's kind of arbitrary, but it allows us to kind of view and put our own limits on, you know, the cost of this function, and gives us an idea of cost of an algorithm. All right. So that is this was our bubble sort. So we'll put that back down to 1, and then selection sort, we'll put that back down to 1 as well. And what else do we need to do? So the sort succeeded, and we need to think about the time complexity here. So the time complexity, we have sort of the same thing we've had in all of the sorting algorithms so far, right? We have a for loop that goes to approximately n, you know, the length of the sorted list, which is n. And then we have another list inside that is based on the length of the sorted list, or I. You know, since I is based on the length of the sorted list, that's the same thing. So these essentially, you got 2 for loops that are based on n. So that's basically n times n, right? So that is n squared. All right, all of the algorithms we've looked at so far have been n squared. So we look at this, the time complexity of this is n squared. All right, and we can run this one last time. Selection, and we can try it with a few more numbers. And then we'll add a big number down here and a small number down there. Okay, and so it took 101 units of work, and we could try that with bubble sort. Bubble sort took 131, and that's not even with our changing our swap function. And then we can look at insertion sort. Units. So for that particular list, insertion sort seems to be the most efficient. But it always depends on the type of data that you start with. And generally speaking, you don't know exactly the type of data that you're starting with. You might know something about it, and that can help you choose which sorting algorithm you want to use. If the data is mostly sorted, for example, maybe only a few new items have been added, but it started out as a sorted list, but then a few items got added in there, you might choose a different algorithm because certain algorithms might be much, much faster if the list is partially sorted, right? So if you know anything about your data, it helps. But for these algorithms, we're just assuming random data. And we could even do that. We could make a loop, and instead of collecting the data manually like this, we could just randomly generate a bunch of data in a list and sort that data and test it against the Python sorted data to see if it succeeded. Okay, so I'll leave that exercise to you. So this has been selection sort.